Good day, good morning, good afternoon, good evening, estudiantes de AP Chemistry. We are covering topics 8.1, 8.2, and 8.3. I will do some practice problems from each of these topics for you, and then I'm going to ask you to do some practice on your own, because that's how you get better. I do, we do, and you do. Sometimes I do the you do with you, but I'll give you other you do. So 8.1, I should just say all of Unit 8 is about acids and bases, which just zoom out for a second and realize that life exists within this narrow range of hydrogen ion concentration, and thus understanding the system, which these are all equilibrium systems of hydrogen ions, is important to doing science, whether it's biological sciences or environmental sciences. Having a thorough understanding of pH and pH systems, and with that comes buffers, is central to understanding how the world works. So some of this first bit is review, because we covered some acid-base chemistry in Unit 4. And so if it seems like you might have learned a couple of these things before, it's because you have. And so we'll kind of go through them quickly, but then we'll be adding on another layer, and that's treating a lot of these problems as equilibrium problems. And because now that we have discussed equilibrium, we can dive deeper into acids and bases. So we'll start with 8.1. I'd encourage you just to pause and read through the notes before I kind of read through them with you. But if you just want to read through them with me, that's fine as well. I'll point out the important things, but if you're not understanding anything, then stop, pause, and read through things. And as with always the practice problems, I'm just going to encourage you guys to give them a shot before I actually solve them out. Okay, so let's get going here. So we'll just start with our note section right here. So it says in Unit 4.8, we introduced the concepts of acids and bases, and that's what I was just saying. We looked at acids and bases and how we identify conjugate acids and bases, and we even introduced some pH calculations. When we're doing these problems, the equations that you're given on the exam, you're given the equation to calculate pH, which is negative log of the hydronium ion concentration. Remember that hydronium ion is interchangeable and either is appropriate for the AP exam with the hydrogen ion, but the hydronium ion is a better representation of what is actually happening in solution, because it's this hydrogen ion combines with water to form the hydronium ion. So given the pH is the negative log base 10 of the hydronium ion concentration, and then the pOH is the negative log of the hydroxide ion concentration. We're also given this new one, which is the KW expression, and we'll talk about what that is, and then also what the pKW expression is, and we'll come back to that as well. So remember that acids are hydrogen ion donors, and bases are hydrogen ion acceptors. So when acids and bases are discussed, their pH is often referenced. It's a way to describe how acidic or basic a substance is, right? And that's pH is just the mathematical concentration of the hydrogen ions or the hydronium ions in solution. And so when we say the pH of pure water is 7, that's at 25 degrees. And so at 25 degrees, we know that acids have a higher concentration of hydronium ions, which means the pH is less than 7. Since it's a negative log of the hydrogen ion concentration, whenever we put a P in front of something, it's the inverse. So getting a number that is smaller means a concentration that is higher, and getting a number that is larger means getting a concentration that is lesser. So we also know that acids have a OH minus concentration, which is the opposite of H plus or hydronium ion, is pH of greater than 7. If it's neutral, we always know that the pH and the pOH at 25 degrees is equal to 7. And bases, we know that if their hydrogen ion concentration is less than 10 to the minus 7, and thus their pH is greater than 7, and their pOH is less than 7. As we have mentioned before, the acid-base scale can go beyond 0 to 14. Here's just an example right here. The pH of 12 molar hydrochloric acid, that's the stock solution of hydrochloric acid. If you do the math on that, the negative log of 12 actually comes out to negative 1.079. So then the pH of a 1 molar solution of a strong acid is 0, but anything greater than a 1 molar solution of a strong acid will actually be a negative concentration. So let's get to where pH actually comes from. I think sometimes this discussion gets lost. In water at 25 degrees Celsius, we have this thing called autoionization happen. And that means that for every 2 water molecules, 1 out of 10 billion of those water molecules gains a hydrogen ion, and 1 out of 10 billion of those water molecules loses a hydrogen ion. And so that means that and I'm going to just zoom in so I can write it here, at 25 degrees Celsius, the hydrogen ion concentration of the solution is 1 times 10 to the minus 7, and the hydroxide ion concentration of the solution is 1 times 10 to the minus 7. So this is actually an equilibrium system, and so we could actually write this as an equilibrium expression, and if we do that, we call it Kw. That's the K for water, and that's equal to the hydronium ion concentration, the hydroxide ion concentration over, it's over nothing because water is a liquid and we don't include liquids in the equilibrium expression. So that means that we can say at 25 degrees, Kw is equal to 1 times 10 to the minus 14, which is equal to this expression. And that'll help us with a lot of our calculations. And again, you could simplify this as just Kw equals the hydrogen ion concentration times the hydroxide ion concentration. But as the notes mention here, hydronium ion concentration is preferred. Okay, so what does that mean? That means that we have, oh yes, remember this puppy right here, our little box that shows us how to convert between pH, pOH, OH minus, and H plus. And now we have added in this little conversion, which you could have done it in 3 steps, but now you can just do it in 1. And that's that if you know the if you know the hydroxide ion concentration, you can calculate the hydrogen ion concentration by just taking Kw, which is 1 times 10 to the minus 14, divided by OH minus. And you can do the same with the hydrogen ion concentration if you know that, and you want to solve for the hydroxide ion concentration. So guess what? Equilibriums. K's can shift, okay? I should just mention right here in this box, mentions pKw. Whenever you see a P in front of something, that's just 10 to the minus. So sometimes we'll be given Kw values, but just to simplify them and put them in like not 1 times 10 to the minus 14 numbers, often we'll just express them as pKws. And so the pKw of water at 25 degrees is 14, which pKw, just to derive this, is equal to the negative log of Kw. Okay, so whenever you see that, that's what it's referring to. So like we'll look at Ka and Kbs, and then sometimes those will be expressed as pKas and pKbs. Okay, so this auto dissociation of water is temperature dependent, like most other equilibriums. And so that means that if we add heat, the equilibrium will shift. Now, sometimes the AP question is this an endo or an exothermic process? Well, you can either just memorize that the autoionization of water is an endothermic process, or you could be given data and told to analyze it. So if you know that it's an endothermic process, that means that as we heat water up, more of the molecules are going to dissociate. So the concentration of both H3O plus and OH minus goes up, which means pH and pOH, as you increase temperature, both go down. Now, that doesn't mean that the solution is not neutral, because they are both going down equally, right? So you could actually have water that is neutral with a pH of, let's say, 6, if the hydrogen ion concentration was 10 to the minus 6, but then the hydroxide ion concentration would also be 10 to the minus 6, so the solution would still be neutral. So this 7 thing is just tied to water at 25 degrees. The opposite would be true if we cool it off. As we cool it off, the pH and the pOH would actually both go up, because the concentration of H3O plus and OH minus would go down. And so here we see what is written, and this is pretty much just summarizing that in this paragraph. And then here we can see, as water goes from 0 to 40 degrees Celsius, right, the H3O plus and the OH minus concentrations go from 10 to the minus 8th to 1.7 times 10 to the minus 7. So that means it's getting larger, right? So there's more H3O plus and OH minus, which means the pH is getting smaller, since it's the negative log of the hydroxide, or of the hydrogen ion concentration. And that means Kw also changes, because it's just the product of the hydronium and the hydroxide ion concentration. And it goes, it gradually gets bigger. So as you warm water up, the Kw gets larger, which means the pKw gets smaller. Okay, then a couple of last little just reminders here. Fig rule for pH. Only the numbers after the decimal point matter, okay? The rest is part of the base 10 part of the equation, so those don't matter. And then also, as a reminder, you guys need to memorize your strong acids and your strong bases. The strong acids, here's one mnemonic for memorizing. So I brought no clean clothes. Okay, well, maybe that helps for you. Maybe it doesn't, but hydrochloric, hydroiodic, hydrobromic, nitric, sulfuric acid, and also perchloric acid. Those are our 6 strong bases. The 6 strong acids. The strong bases are basically the metal hydroxides, where the metal, it comes from group 1, your alkali metals, or group 2, your alkaline earth metals. Okay, let me just do a quick little time check here. So now would be a great time for you to just pause and see if you could do some of these problems. What I'm going to recommend is this we do problem. It's going to make a lot more sense after we actually cover section 8.3. So I'm going to say maybe you could just bypass that problem. Let me just pick a few of these to do with you, though. And then you'll see this has a lot of overlap with section 8.2. So what is the pH of a 0.325 molar potassium hydroxide solution? Well, we know that this is a base, a strong base. And so if we take the OH minus concentration is the concentration of the base, since it fully dissociates, right? That's what strong bases do. And so if we take the negative log of 0.325 molar, that's going to equal my OH minus concentration. And when we, sorry, that makes no sense. I got to step ahead of myself there. So the OH minus concentration is 0.325 molar, since all of the potassium hydroxide dissociates, equals 0.325 molar. And then if we take the negative log of that, that's going to give us our pOH, since that's our OH minus concentration. The pOH is the negative log of 0.325, which gives us 0.488. That is the pOH. And the pH thus is just 14 minus 0.488, which is equal to 13.512. Keep in mind, I kept my 3 sig figs because it's only the numbers past the decimal point. Okay, let's look at our next one here. Here we made a solution using sodium hydroxide. The pH was found to be this. What is the concentration of the hydroxide ion concentration? Okay, so that's our pH, and it's asking for the hydroxide ion concentration. So the first thing I would do is I would figure out what is POH. So POH is just 14 minus 11.452. And then if you guys remember, the OH minus concentration is going to be 10 to the minus POH, which is 10 to the minus 2.548. And when we figure that out, we get 2.83, right? I'm taking these 3 sig figs times 10 to the minus 3 molar. Okay. Next one here. Ooh, we're back to KSP. Yes. So a solution of silver nitrate is added to lithium hydroxide. The KSP of silver hydroxide is really small. That's what it's telling us. What happens with the pH as the silver nitrate is added? Okay, think about this. As we add silver nitrate, silver's going to be combining with OH minus. And when that happens, the vast majority, because the KSP is really small, is going to precipitate out. And so a lot of AgOH will form. And so there will be less OH minus in the solution. So that means the solution will become less basic or more acidic. So the pH decreases. Okay. If we were asked to find, tells us the kW of water at 50 degrees Celsius. I'll just kind of set this up for you and then let you figure it out. It asks for the pH and the POH. We know the kW expression is OH minus times H plus, and basically it's telling us at this temperature it's equal to 5.476 times 10 to the minus 14. So we can just solve, make those both X, right? And we can say that if this is X and this is X, and then we can just solve for X is equal to the root of 5.476 times 10 to the minus 14. And then we can solve for that X and then take the negative log with those values, and that will give us both the pH and the POH, which I believe you get 6.6308. One last little one I did just want to look at. So I'm going to ask you to complete the rest of these on your own and then check the answer key, which will be up online shortly. But if we look at number 6 here, it says, what would happen if we added, so we have this solution, this acid, and then we have 20 mils of it. It has a pH of 5, okay? So it says, first of all, what happened if we added 180 milliliters of distilled water? So that means the volume would go from 20 to 200 milliliters. So that means it would be a 10 times dilution. Every time we dilute an acid by 10 times, at least until we get to a pH of 7, the pH is going to go up by 1 because the hydrogen ion concentration has changed by a factor of 10. Again, that is until we get to the pH of 7, which we can talk more about that. And so that means that if we took this acid and went from 20 to 200 mils, the new pH would be 6.00. And then in this one here, we're going from 20 to 2,000 milliliters. And so that's a change of 100 times dilution. And so that would be a pH of 7.00. Okay. And then this last one here is just saying once we get to a pH of 7, there's no more change. So in this case, you get adding more water does not change the pH. Change pH. That's a little change sign. Okay, so let's go ahead and go to our next topic here. Next topic is kind of something we just did. It's just separating out the pH and the pOH of strong acids and bases. And so I'm going to go ahead. You guys can go ahead and read through this. There's just a couple of little additions here. We're just reminded of what the main strong acids are. We're reminded that they are strong electrolytes. That means when you add them to solution, since they dissociate into ions, they conduct electricity in the aqueous form. And then we're also reminded that for strong acids, the concentration of the acid is equal to the concentration of the hydronium ions. And that also for H2SO4, it's only strong with respect to the first proton coming off. When it does, however, react with a base, as in would with a titration, both hydrogen ions do eventually come off. And we'll get more to that when we talk about titrations. Strong bases, we just identified what those are. And we also just did practice with the pH calculations and the calculations of pOH. And then we're also just reminded that pOH plus pOH at 25 degrees is equal to 14. And then with this example here, I just kind of wanted to just show you this one here. Just a reminder, this says, what is the pH of a 0.01 molar solution of barium hydroxide? Well, since it's barium hydroxide, that means it's Ba2+, and then it has 2 hydroxides. Both of those come off. And so the concentration of the hydroxide ion is twice the concentration of the solution, okay? And so the pOH is equal to the negative log of the hydroxide ion concentration, which is 1.7. And so the pOH is 14 minus that, which comes out to 12.30. Okay, so all of these are very, very similar to the ones that we just did, but I would like you to do them and then to check your work. If you're asking a question like which of these is a strong electrolyte, that's just asking you, can you identify your strong acids and your strong bases? And then for something like this, why does a 0.01 molar solution of hydrochloric acid have a pH of 2, but one of another acid like acetic acid, K vinegar, is 3.37, and that's just because it's a weak acid, so it only partially dissociates. And if you're wondering, well, how do I figure out the pH of a weak acid? Oh, baby, ice, baby, is back. So let's go ahead, and if you haven't already paused, pause and just complete these 6 problems to make sure you are proficient with this type of problem. And now let's get to weak acid and base equilibrium. Just going to take a quick second here to make sure we are all good and that everything is sharing. You didn't notice I'm in my truck today, actually. That is because I went to my classroom to make this video, and go figure, there was no internet. So here I am in my truck on a hotspot because I have no internet at home either. But I was determined, I say, to get this video done. Okay, so here we go. Lots of new stuff with this one. Okay. Okay. So we're given a few more equations here. We're talking about the pH of weak acids or weak bases. We have to figure out, well, how weak are they? And the way the relative weakness or strength, however you want to say it, of an acid or base is communicated is by this number called the Ka, which you guys know Ka is the equilibrium expression for acids and bases. And so we'll look at how we derive these equations in just a second. But for acids, we express a Ka value, which that can also be expressed as a pKa value, which remember, as a Ka value gets smaller, the pKa value gets bigger. Or for bases, we express the strength or relative weakness of a base in Kb or pKb. And the same is true. The smaller the Kb, the larger the pKb. Okay, so we've talked about our 6 strong acids, but if it's not a strong acid, okay, then the acid, which is represented by Ha, when it joins with water, it's going to be in equilibrium with H3O plus A minus, which is the conjugate base of the acid, okay? And so that means that if we were to write the K expression for this, which since it's an acid, we call it the Ka, it's equal to the H3O plus times the A minus, which those are going to be equal because to form the H3O plus, you have to lose the hydrogen ion, and to form the A minus, something that's its conjugate base. And so these concentrations are always going to be equal, and then over Ha. So that's our, and then we don't include water because it's a liquid. That is our expression for acids. Okay, so we call that the Ka. And so since these constants are generally very small, the pKa is often reported instead of the Ka. For acids, the smaller the Ka, the larger the pKa, the weaker the acid. So small Ka, large pKa, the weaker the acid. A weak acid will exist primarily in its molecular form. That means the form that is undissociated in solution. And so if you're looking at like an acid, and this from an AP diagram right here, the way you tell that this is a weak acid is Ha is the acid, and you can see most of the Ha particles, I'm just going to point to a few of them, are undissociated. There's only one Ha particle, right? This would be our A minus. This is our hydronium ion that has actually dissociated. And so since most of the HA molecules remain intact and only a few ionize, that would be the diagram for a weak acid. The weaker the acid, the less ionization there is in solution. And we'll actually look at how we can determine percent ionization here in just a minute as well. So weak bases, those are anything that's aren't a strong base. And so we can write out the dissociation of a weak base like this, where B is the base, and Kb in this case is equal to the Hb plus times the OH minus, where the Hb plus, if you think about that, that's just the conjugate base, sorry, the conjugate acid, and then this is the base, right? And so Hb plus times OH minus over the concentration of the base. So that's our equilibrium expression for Kb. And again, let's see. Often Kb is reported, okay, because these values are very small. So for bases, the smaller the Kb is, right, the weaker the base and the larger the pKb. So larger pKb and smaller Kb, that means a weaker base. So a weak base will exist primarily in its ununionized form or unionized form in solution. Okay, just to kind of prove this whole thing in your head, the smaller the Kb. So let's just write one out, right? So let's just say the OH, or so let's say we have a really weak base. Let's say it's like 10 to the minus 15 is the Kb, right? So that means barely any dissociation happens. But that would mean the pKb would be 15, which would be really big. And so this would be numbers associated with a really weak base. Okay. And then there's one last, and this is just a similar diagram as the one we saw above. But again, this is just showing a weak base, and it's showing the base particles. Not many of them have picked up a hydrogen ion. And so not many hydroxide ions have formed, only that one hydroxide ion formed. And remember that for this to happen, so right, these OH minus and the HB plus, those will always be equal in solution. So there's one other equation associated with topic 8.3, and that is also just fun one. It's percent ionization. So it's just another way to express the extent of the ionization of an acid or a base. And so a strong acid has 100% ionization, and a weak acid has a lower percent ionization. And the way we express percent ionization is it's equal to the H3O concentration after the acid had dissociated over the initial concentration of the acid, where the acid is HA times 100%. Okay, so how do we do these equations then? Well, here's where it all comes back to things that we learned in Unit 7. So here we're given, let's just step through this I do one here. We're given the pKa of hypochlorous acid is 7.54. And then we're asked, what is the pH of a 0.1 molar solution of HClO? So HClO, you have to first recognize that's a weak acid because it's not one of the 6 strong acids. Okay, and we're given pKa. All right, so first thing I do is figure out, okay, so in solution, this HClO is going to combine with water, and it'll form a hydronium ion plus the conjugate base of HClO, which is ClO minus. Okay, so the equilibrium expression is going to be H3O plus, so it's an acid, right? So it's a Ka. So it's going to be the H3O plus times the conjugate base, which is going to be ClO minus over HClO, right? So for Ka, it's always going to be this guy on the bottom and these two things on the top. Okay, so Ka can be calculated from pKa because we need it to be in Ka values to do these problems. Okay, so the first thing I'm going to do is just convert pKa to Ka. So pKa is the negative log of the Ka, and thus Ka is equal to 10. I'll just write it over here. Ka is equal to 10 to the minus pKa. And so we get that the Ka is that right there, which how can that be helpful? Say, so weak acid, weak base problem, you're going to set up an ice table, right? So we know the initial concentration of the weak acid is 0.1. We know the initial concentration before dissociation, the hydronium and the conjugate base is 0. We know this one is going to go down by X. That's our change. We know these are going to both go up by X. And so then we know our equilibrium concentrations. This should look very familiar. So we can rearrange the Ka expression where 2.9 times 10 to the minus 8, the Ka is equal to X times X, the hydronium ion concentration times the conjugate base concentration, over 0.100 minus X on all of these problems. At this point, I'm just going to put, you can use the solver function, which actually I have a printout for you on how to do that. But you can solve the equation using the equation solver, or since Ka is very small, we can assume that X is very small, negligible, less than 5%, and we can ignore X when solving. So when we rearrange this, we solve for X. And now remember that X is the hydrogen ion concentration. So we can go ahead and we can solve for X, and we get the hydrogen ion concentration is 5.4 times 10 to the minus 5. Question's asking what's the pH, so we have to take the negative log of the hydronium ion concentration, and we get a pH of 4.27. This here just shows how to actually like check to make sure that we met the 5% rule. Okay, so let's just do a couple of these together, and then I'm going to let you do the rest alone. So the first one here, the you do here, which species exist in the highest concentration in 0.100 molar solution of nitrous acid? So this is it's a qualitative, not a quantitative question. So remember that for a weak acid, and you can tell it's a weak acid because it has a K of 10 to the minus 4, that means not much of the acid itself dissociates. Only a very small percentage of the acid actually dissociates. And so that means that in this solution, there's not much H3O plus, there's not much NO2 minus, but there's still a lot of this in the undissociated form. So that would be in the highest concentration. Okay, let's do one that says, what's the pH of a 0.785 molar solution of formic acid? Okay, so first thing, and it gives me the Ka of the formic acid. So I'm going to go ahead and I'm just going to write this out. So formic acid is HCHO2, and then I'm just going to write it without the water there to shortcut it, is going to be in equilibrium with H3O plus. These are all in aqueous states times CHO2 minus, right? That's the acid and then the conjugate base, right? And then I know the Ka, I'm solving for the pH. So I'm going to set up my ice table so I can figure out my hydrogen ion concentration. The initial is 0.785 molar. This is going to go down by X. It's going to be a very small number because it's 10 to the minus 4, so I'll probably just ignore that. So this equilibrium concentration is 0.785 molar minus X. These both start at 0, and then they're going to go up by X and up by X. And so our equilibrium concentration is X and X. And then I know the Ka is going to just be equal to then X times X, right? Hydronium ions concentration times the conjugate base over 0.785 molar minus X. And I know that this is equal to 1.77 times 10 to the minus 4 molar. And now I just solve for X. Remember, X is equal to the H3O plus concentration. And I get that X is equal to 0.0117 molar. And remember, that's the hydrogen ion concentration. It's asking for pH, so I just need to do the pH is equal to the negative log of 0.0117 molar. And I get the pH is equal to 1.932. Bada bing, bada boom. For this next one here, it gives me the Kb, which means I must be dealing with a base. Methylamine, nitrogenous bases. It's very common that you see these types of ones here. So let's just write it out. So we have methylamine, CH3NH2. That means that it's going to be in, I'll just write it out, with water so we can kind of see the whole thing here. It's going to accept a hydrogen ion, which means it's going to be CH3NH3 with a plus sign, plus OH minus, right? And then the ice table here would just be, let's see, our initial concentration is 0.250. It's going to be minus X of 0.250 minus X. It's going to be 0 and 0, and then plus X, and eventually you don't have to be writing out these ice tables every single time. And we can ignore the minus the X because it's small, 10 to the minus 4, so that's within the 5% rule. And so we just set this up and we can say, so X squared over 250 is equal to the Kb, which is 4.47 times 10 to the minus 4. And the thing we have to remember is here, since it's a Kb, the X is the OH minus concentration. And so when we figure that out, we get X is equal to X is equal to, 0.0104 molar, which that's the hydroxide ion concentration. So the negative log of that is the OH, which is 1.983. And then we finally get the pH, 14 minus that is equal to 12.017. Okay. If we were given something like this. What is the pH of a solution of phenol? And it gives us the pKa. The thing we have to just remember is that one of the first things we have to do is we just have to turn the pKa into the Ka value first. And so just remember Ka is equal to 10 to the minus pKa. Okay. So I'm going to let you go ahead and solve the rest of these. One that you might see, it is an interesting one here, is something like, so there's a percent ionization one here, and it's really important to go through these. These are really common ones on the AP test. But here, right, you might wonder, how do we figure this out? Here you're given the pH and you're told to solve for the pKa. And so you can actually just use the Ka expression, right? And since we know the pH is that, then we can figure out the H plus. So like for this particular one, right, it's just a generic acid. So it's the Ka is equal to H plus times times the conjugate base concentration just over the acid concentration. And we know that these two are equal, and we can figure out the H plus by just taking 10 to the minus pH. So like we would just say Ka equals 10 to the minus 2.51. And we would just basically square that and then over 0.150. And that'll give us the Ka. And then if we just take the negative log of that, so the negative log of this, that will give us the pKa. Okay. So please go ahead, finish the rest of these. It is important that you finish the rest of these, finish the rest of all of these, and then check with your answer keys and make sure that you are understanding these, because we are going to jump to the next topic. And this is your major instruction for topics 8.1, 8.2, and 8.3. Sorry it was so long, but just lots of information to cover. Take care, everybody. Hope that was helpful.